Good morning. The topic for this lesson is equations of tangent lines. And I want to begin just by reviewing some information with you. First of all, the derivative dy by dx, or y prime, is the instantaneous rate of change in y with respect to x. And we've reviewed some examples of this already. In the last unit, we looked at ds by dt, which was the rate of change in displacement with respect to time, and that was equal to the velocity. We also looked at dv by dt, which was the instantaneous rate of change in velocity with respect to time and was equal to the acceleration. We considered related rate problems as well. And again, with the related rates problems, we had dt here for two quantities. So what I want to do today is look at the graphical interpretation of this. And we know that change in y over change in x is equal to slope. So if we're talking about now the instantaneous rate of change in y with respect to x, this now means like an instantaneous slope, or in other words, dy by dx is the slope of the tangent line to the curve. Now, you may hopefully remember what a tangent line is. It is true that a tangent line intersects the curve at exactly one point. So we say one and only one point. And I wanted to remind you just how we can go about finding the equation of a straight line. You would have reviewed this in your second math course. Actually, no, your first math course, and it's called point slope equation. So all you need to know is the slope of the line and any one point on the line, and then you can use this equation in order to come up with the equation of the straight line. And of course here the x and y remain as variables. Okay, so all we need is one specific point given by x1, y1, and also the slope given by m. Okay, so I want to take all this information now and go about solving some examples with you, okay? All right, so we're gonna get started with this example here in just one moment. Okay, so let's read the question. It says, determine the equation of the tangent line to y equals x cubed minus 3x at x equals 2. Now remember, in order to determine the equation of the line, we need both a slope and a point. Now, thus far, we know an x value. So we can begin by finding the y value that would go with this x value. And you know that that's done simply by substituting into the equation. So we can say when we use an x1 value of 2, what will y1 be? So y1 will be 2 cubed minus 3 times 2. In other words, it's going to be 8 minus 6, or 2. So now we have the point of interest, and it's the point 2, 2. Okay, now that we have a point, we need the slope of the tangent line. And we were just reviewing the fact that the slope of the tangent line is given by the derivative. So we should definitely form the derivative. And here you can use dy by dx, or you can use y prime. So the derivative of this binomial is just 3x squared minus 3. So this is an expression for the slope of the tangent line to the curve at any point. If we want to know the slope of the tangent line at this point, well, once again, we're going to substitute that same x value given here. Okay, so we can say when the x1 value is 2, we arrive at dy by dx is 3 times 2 squared minus 3. This is 12 minus 3, or 9. And now we're all set. This is what we'll use for our slope, and this is what we'll use for our point. And remember, the equation looks like this. Oops, that's just supposed to be y minus y1, x minus x1. Be right back, sorry. I think I'd remember to keep this with me by now. There we go. Okay, so the equation that we're using is point slope form, y minus y1 over x minus x1. Okay, so the slope is substituted on the left side, and in this case it is 9. And now we do y minus, the y1 value is 2 over x minus the x1 value is also 2, like this. So now we have it substituted. We're just going to put this in general form. Okay, so we begin by cross multiplying here like this. So 9 times x minus 2 is y minus 2. So this will be 9x minus 18 is y minus 2. Lastly, we're going to put all terms on the left side, making the right side 0. So 9x minus y. So it's negative 18, and it'll be plus 2. So minus 16 is equal to 0. So this equation is called general form. It's when we have right side equal to 0. Some of you like to put it into the form y equals mx plus b as well, and that I guess would be y equals 9x minus 16. Either way, it describes the same straight line. Okay, so I just want to take a moment to review the graph with you, okay? So here's what we did in this problem. Y equals x cubed minus 3x is this function graphed here. The cubic function has a maximum point and a minimum point, okay? So that's the cubic function. Now, at the point 2, 2, so I've put a dot here at the point 2, 2, a tangent line is drawn. So you should see a straight line drawn. Now again, remember the key is that the straight line intersects the graph at only that point. And that's, not easy to see in this particular diagram, but the cubic function and the straight line intersect only at the point 2, 2. Okay, so that straight line there has this equation. 9x minus y minus 16 is 0. The slope of that straight line is 9. Okay, so we're going to go on and solve another question. So let me just get our second one here set up. All right, so determine the equation of the tangent line to y equals 4 over 5 minus 2x all squared, where x is 2. And we can follow the exact same process. So first of all, we're given an x1 value. It happens to be 2 again. So what we're going to do is find the y value that goes with it so that we have an ordered pair. Okay, so we can say when the x1 value is 2, what will y1 be? Well, it will be 4 over, so in here we're substituting 2, so it's 5 minus 2 times 2 all squared, which is in the denominator there 5 minus 4 or 1 squared. So you get 4 over 1 or 4. And so this means the ordered pair x1, y1 is 2, 4. So this is x1 and this is y1 and this is the point of interest. Okay, once you have a point of interest, remember that you also need the slope of the line. The slope of the line is the derivative of this function. So we need to form y prime. Now, how will we do that? This is not a polynomial. In fact, we can't take the derivative with the variable in the denominator like this. So what we do is we bring that up and write it this way with a negative exponent. So this is simply rewriting the function. Okay, so it's still y. And now we find y prime or dy by dx by using our chain rule. So the negative 2 comes forward and multiplies by 4 to give us negative 8. We subtract 1 from the given exponent. So if it was negative 2, it's now negative 3. And we multiply by the derivative of the inside of the bracket here. What is the derivative of 5 minus 2x? Well, it is 0 minus 2. In other words, it's negative 2. So rewriting this now, negative 8 times negative 2 is 16. So we have 16 times 5 minus 2x to the negative 3, or 16 over 5 minus 2x all cubed. So this is an expression for the first derivative. It is an expression that provides the slope of the tangent line at any point along the curve. Okay? We need a numeric value, which means we actually have to substitute an x value in here. And of course, we use the given x value. So we can say here, when x1 is 2, the derivative is equal to 16 over 5 minus 2 times 2 all cubed. So we substitute x is 2. Now again, this is 1 cubed in the denominator. So we get 16 over 1. The slope of the tangent line to the original curve is equal to 16 when x is 2. And now we simply go back to our point slope form equation. We're going to substitute 16 here. For x1, we use the given value of 2, and for y1, we use the value 4 that we calculated. X and y remain as the variables. So 16 is y minus 4 over x minus 2, like this. Cross multiply next. Okay, so we're gonna have 16 times x minus 2 is y minus 4. 16x minus 32 is y minus 4. And then again, for general form, we put everything on one side with right side 0. So 16x minus y. Now it's negative 32 plus 4. So negative 28 is 0. And again, that's the same as y equals 16x minus 28. If you write it in the form y equals mx plus b instead. Okay, so again, you're given an x value, find the corresponding y value. Take the function and find its derivative. Evaluate its derivative at the given x value. And then substitute into point slope form. All right, so here is the graph. We'll take a couple moments to review the graph. Now, this curve is hyperbolic. Okay, so it's going to be detailed by two main pieces. The fact is it has a vertical asymptote. So this function is not defined when x is 2.5. Because when x is 2.5, you would get a denominator of 0 here. So down below in the graph, this right here, what I'm pointing at, this is called, so I'll do this, make a broken line all the way down. This is the vertical asymptote at x is equal to 2.5. That's the equation of that vertical line. X is equal to 2.5. Maybe I can just add that here. And then we also have a horizontal one at y equals 0. So that's another line that the graph would never cross, is the line y equals 0. That's the horizontal asymptote. And that's because there's nothing you could substitute for x here that would give you a y value equal to 0. In order to get an answer of 0 here, the denominator would have to be infinitely large. Okay, so anyway, there's also that broken line then at the y-axis, like this. Okay, and then the two pieces of the graph, therefore, are here and here. Okay, so the curve will approach these two lines but never touch it. Okay, the point of interest is 2, 4, and I've drawn a dot at the point 2, 4 right there on the graph. And at that point, a tangent line is drawn. Can you see the tangent line drawn there, the straight line drawn? And all we did was determine the equation of that straight line, and it is right here. Okay? Okay, and I know you're thinking, am I going to be required to draw these diagrams? And no, I will not ask you to draw the diagrams, but I do need you to begin to understand them. Okay, so let's go on and do one more example together. Find the equation of the tangent line to 16x squared plus 9y squared is 145 at the point 2, 3. So interestingly, this time, not only are we given an x value, but we're also given the corresponding y value. So that's interesting. We already therefore know not only x1, but also y1. So that's going to actually cut down on our work. We'll have to talk about why that is, perhaps when we get to look at the graph, okay? All right, so anyway, let's begin, therefore, with the derivative. Since we already know the corresponding y value, we can start at the point where we find dy by dx or y prime. Now, this is not of the form y equals some function of x. Okay, so we don't have y isolated, in other words. So you might recall that in a case like this, it's often simplest to use implicit differentiation. So let's do that here. We're going to take the derivative term by term, left to right. So let's start here with 16x squared. Its derivative is 32x. We put in our plus sign. Now, what is the derivative of 9y squared? Well, it's 18y times dy by dx. Okay, or 18y times y prime. Put in your equal sign. Don't forget, you also have to differentiate the right side. In this case, the derivative of the number 145 is 0. So we end up with this 32x plus 18y times dy by dx, this is multiplication, is 0. And anyway, what is our objective now? We're supposed to get our expression for dy by dx. So I've got to isolate this right here. How do I do that correctly? Well, first I move this term. So we have 18y times dy by dx is equal to negative 32x. Now I divide. Dy by dx then is equal to negative 32x over 18y. And this is something that can be reduced, okay, because both of these numbers are divisible by 2. So we can make this negative 16x over 9y. Okay, so what is this? This is an expression for the slope of the tangent line to the given curve at all points on the curve. Okay, but remember, we need a numeric value. What does that mean this time? It means not only do we have to substitute an x value, but we also have to substitute a y value. So let's do that. At the point 2, 3, what's going to happen? Dy by dx will equal negative 16 times 2 over 9 times 3. And that is negative 32 over 27. And now we have everything that we need. We, of course, will use this as m. We will use our 2 as x1, our 3 as y1. So all that remains is substitution into this point slope form. So again, negative 32 over 27 is m. y1 is 3, and x1 is 2. We're going to cross multiply. Now you could go this way first or this way first. I'm going to go like this. 27 times y minus 3 is negative 32 times x minus 2. So now we'll have 27y minus 81 equals negative 32x plus 64. And for general form, put everything onto that left side. 27y plus 32x minus 145 is equal to 0. Okay, now I should point out that this, of course, is exactly the same as the equation having negative 27y, negative 32x, and positive 145 is 0. even if the terms here were in a different order. So negative 32x, negative 27y plus 145 is 0. Those are all the same straight line equations, okay? And you would have a different looking answer if, for example, I cross multiplied this way first, putting that on the left side. Okay, so any linear multiple of this would describe the same straight line. So when you're checking your answers in this unit, if you have the same answer but with all signs different, then you also have the correct answer. Okay, let's talk about the graph. This equation right here describes an ellipse. So here is the ellipse drawn in the graph. Now, remember the discussion. Why did they give us the value of 3 this time instead of asking us to just calculate that value? Well, here's the truth, and you might be thinking it already. When x is 2, y is equal to 3 or negative 3. So there are 2 possible values for y. Okay, so when x is equal to 2, the point down here would be 2, negative 3. The tangent line there would look like this, right? Okay, so there would be 2 tangent lines drawn when x is equal to 2. So in this case, for clarity, they gave us the full ordered pair, so we knew we were trying to determine the equation of this tangent line right here. Okay, and we did. Its equation, the equation of the tangent line right there, is 27y plus 32x minus 145 is 0. Okay, and it's the line with slope negative 32 over 27. And you can see what would happen if in fact, we were using the point down here. The point would be 2, negative 3. So you'd be substituting 2 and negative 3 up here, and you'd get the same slope, but it would be with a positive sign. So the slope down here of the tangent line to the ellipse would have the same magnitude but opposite sign. Okay, so looking back, we did 3 examples where we found the equation of the tangent line, one where we took the derivative of a polynomial, one where the derivative required us to use a chain rule, and one where we found the derivative implicitly. Okay, so I've got some suggested practice problems for you listed in Blackboard. Have a great day.